Hello, welcome to a video on the last page of section 6.2 regarding anti-differentiation using substitution. So for these two examples, 11 and 12, we're going to be talking about how to use substitution for definite integrals. Previously, we talked about how to do substitution for indefinite integrals, but it's going to be a little different for definite integrals. So if you use substitution, you must change the limits of integration. That is going to be very, very important. So let's take a look at what's happening here. We have tangent x times secant squared x dx. Okay, so I'm going to rewrite this in this manner. I'm going to do tangent x times secant x times secant x dx. Now hopefully you recognize that if we let u equal secant x, that d over dx will be secant x times tan x. Hopefully you can see that. And if I multiply both sides by dx, secant x times tangent x dx is what d is going to equal. Now, before I make the substitution, another thing we need to keep in mind is that our limits of integration must change as well. Because right now, we're assuming that we're integrating with respect to x. So, if x equals pi over 3, then u is going to equal the secant of pi over 3. And if you use your unit circle correctly, cosine of pi over 3 is 1/2, so that'll be 2. Additionally, if x equals pi over 6, then u equals the secant of pi over 6. Cosine of pi over 6 is root 3 over 2, so if you flip it over, that's 2 over root 3. So, when I rewrite this, I'm now integrating from 2 over root 3 to 2, and those right there is going to be du, and of course secant x is u, so just u times du. And take the antiderivative of u, just u squared over 2. We're putting 2 over root 3 and 2. So now I get 2 squared over 2 minus 2 over root 3 squared over 2, which of course will be 2 minus, so yeah, it's 4/3 when you square 2 over root 3, so 4/6, that'll be 2/3. So you should get 4/3 as your answer. If you wanted to, you could have replaced secant x back for u, and then replace the 2 over root 3 and 2 back to pi over 6 and pi over 3, but why do the extra steps if you don't need to? So you could just leave everything in terms of u, and then just use the new limits to evaluate the definite integral. Here's one more, so we can wrap this up. You have x over x squared minus 5. So I'm going to let u equal x squared minus 5. Usually the rule of thumb is we tend to let the expression with the higher exponent, and if it's in a denominator, it's even better because it means we can use natural log for our antiderivative. That's usually a good idea. So of course du over dx will be 2x. So du equals 2x times dx, and if I kind of just move things around a little bit, x dx of course is du over 2. Also, I must change my limits of integration. If x equals 0, then of course u is going to equal negative 5. Just plug in 0 for x squared minus 5, since that's what u equals. If x equals 1, then u is going to equal negative 4. So now, I'm integrating from negative 5 to negative 4, and the x dx right there becomes d over 2, so 1 over u times d over 2. Move the 1/2 out. Take your antiderivative, 1/2 times natural log absolute value of u, obviously from -5 to -4. It's a good thing you have the absolute value, right? So it's 1/2 times natural log of 4 minus 1/2 times natural log of 5. You can condense it in this manner. 1/2 times natural log of 4, or sorry, factor it like this, and then condense it. Using the quotient property for logarithms. And that would be our exact answer. If you want to give a decimal answer, you can obviously punch in the calculator. So that's how you would work out definite integrals using substitution for integration. So there'll be some problems we'll work on regarding this. Okay, goodbye.